Hello, everyone. I'm Ahmed Abdala. I'm a professor and chair of the chemical engineering program at the College of Science and Engineering in Hamad bin Khalifa University. First, I would like to thank the organizers for the kind invitation. Unfortunately, I'm not able to be physically present at the conference because of the current escalation in our region. Today, I would like to share with you our research effort on enhancing the hydrogen storage and release performance of complex metal hydride using a synergistic approach of catalytic nanoparticles and high surface area nanoconfinement. We all know that our sustainable future relies significantly on renewable energy, but most of the renewable energies have intermittent nature. That's why they're always required to be coupled with an energy storage option. Among the energy storage options, hydrogen actually presents an excellent uh, energy carrier. It's provide a clean energy because it doesn't produce any CO2 emission when it's used as a fuel. It has a high energy density on mass basis, and of course, lower energy density on a volumetric basis. To facilitate and accelerate hydrogen technology, it actually that requires to develop novel materials to store large volume of hydrogen uh, at low cost without significant energy loss to facilitate transportation and long-term stability. This is a recent quote from the World Energy Forum report. So this research that I'm going to report today, I focus basically to develop novel material for hydrogen storage. And there are, of course, multiple options for hydrogen storage. These include physical storage of hydrogen as a gas, for example, which requires significantly high pressure in hundreds of bars. And this has associated challenges with safety, material challenges because hydrogen cause hydrogen embrittlement for most metals. So usually hydrogen is stored basically in composite vessels, basically like carbon reinforced composites, which are quite expensive. And of course, there are safety issues associated with storing at high pressure. To avoid basically storing at high pressure, we can store hydrogen in a liquid form at ambient pressure, but that requires basically quite low temperature, about 20 Kelvin. So there will be significant energy loss because of the thermal losses to the ambient condition, which is at significantly higher temperature than the storage temperature. These two options provides good storage capacity, the physical options, but of course they have challenges in terms of cost, safety, etc. Additionally, we can store hydrogen on materials. So we can store hydrogen on high surface area materials through adsorption on MOF, porous carbon, but these actually work efficiently at low temperature. So again, you need quite low temperature, so you have significant energy loss would be associated. The material cost would be another component. Alternatively, we can chemically store hydrogen in chemical compounds, in what we call chemical hydrides, like you can consider ammonia, which has significantly high hydrogen content of 3/17 kilogram per kilogram, and providing basically significantly high energy density. But of course, we need use catalyst to for the formation of the chemical hydrides and then to decompose the chemical hydrides. So this requires also a high temperature for the desorption or the deactivation of the metal hydride and high pressure for the formation of the metal hydride, of the chemical hydrides. Alternatively, we can use metal hydride. So this would be a metallic crystalline material where hydrogen can be stored either as an interstitial in the cavity of these crystals, or it can actually form intermetallic compounds. So metal hydrides, there are two different types of metal hydride. Depends on the mechanism by which hydrogen basically interact with the metal hydride, with the metal atoms, either an interstitial hydride where we have a metal crystal and the hydrogen basically sits on the cavity in the interstitial cavities of that crystal metal structure. An example of that is lanthanide nickel hydride. The other type of metal hydride is a complex hydride. In complex hydride, we form an anion by metal coordination with hydrogen, and then this anion coordinate with a metal cation to form basically the complex metal hydride. The example of the sodium aluminum hydride, for example. The storage of hydrogen is two steps. The first step is the absorption of hydrogen, the metal hydride, and that's typically usually a relatively rapid step. So we can see here we can reach complete storage based on the material in about 4 or 5 hours. But of course, the dehydrogenation or the release of hydrogen from the metal hydride of the desorption is quite a slow step. It requires more than 24 hours. So the challenge usually is associated with the release, which requires high temperature and also snow kinetics. An example of the complex metal hydrides are these has an ion complex of hydrogen with aluminum, boron, or nitrogen. And then this anion is complexes with metal cation, either a lithium or sodium. So we have a variety of these metal hydrides, and they have storage capacity from 6 to 18% as weight percent of hydrogen, and volumetric capacity close to 100 or sometimes higher than 100 kilogram per meter cube hydrogen. And the challenge is usually associated with the desorption temperature. So this is the temperature, the onset of the desorption temperature, quite high. Most of them are above 200, and only lithium aluminum hydride has a moderate temperature, or relatively lower temperature, about 150 degree. The absorption energy, desorption energy is also significant for most of them. The lithium aluminum hydride has a lower desorption energy of about 10 kilomole per 10 kilojoule per mole. So these complex metal hydrides provide good volumetric and gravimetric storage capacity, but they suffer basically from the high desorption temperature and also the poor desorption kinetic, as I indicated in the previous slide. So that's why they're still actually not used in a commercial scale. So we need to enhance both the desorption, the thermodynamics to reduce the desorption temperature, improve the rate of desorption by enhancing the kinetics. So today we're going to focus on enhancing the lithium aluminum hydride, which is basically an anion of aluminum with coordinating with 4 hydrogen atoms, and then that anion complex with lithium cation, forming a monoclinic crystal structure with a hydrogen capacity of about 10.5% and a decomposition temperature about 150 to 160 degrees. So these, among other, aluminum hydride has the lowest, has the highest storage capacity and intermediate release temperature. So if we can actually reduce the release temperature, the hydrogen release temperature, this would be a significant material. The desorption is actually slow, as we mentioned, because it's a multi-step. So the first step is the melting of the lithium aluminum hydride, and then the hydrogen release take place in 3 steps. The first step release about half of the hydrogen, and the last 2 steps release the other half. of the hydrogen. So the onset starts at 150 and then continues to maybe 400 or more than 400 degree to release the 10.5% hydrogen stored on the metal hydride. To enhance the performance and on the release side, usually there are multiple approaches. One is alloying, and also basically you change the metal composition to make less stable hydride bond, and that basically lowers the desorption energy and the temperature for the release. Another viable approach is the nanostructuring by making the metal hydride smaller size that increase the surface area, reduces the diffusion pathway, and it enhance both the kinetics and also the release temperature, because again the free energy for the equilibrium between the hydride form and the hydrogen free form depends on the size of the metal hydride. Another approach is to use a catalyst to dope basically the metal hydride with a catalyst, usually an iron or nickel based, a transition metal catalyst, which basically facilitate the hydrogen release at low temperature by interacting basically with the metal, with the hydrogen. So it reduces actually the metal hydrogen bond strength, which makes it easier to dehydrogenate. So in this research, we aim to enhance the thermodynamic and kinetic of lithium aluminum hydride for the hydrogen desorption step. And the approach is actually we combine a use of iron-based catalyst and to enhance the catalyst performance by nanostructuring. So we do a nano confinement to reduce the size of the catalyst particles and their dispersion. And also we increase the surface area by supporting the catalyst on a mesoporous carbon. So three significant elements: the catalyzed effect of iron-based nanoparticles, the size reduction, and the high surface area, which give us the good distribution and large loading of the catalyst. The approach to prepare the nano catalyst is using a silica templating method. So first we prepare the silica template using the polyrenic surfactant to form just dissolve it in water basically, and then basically add the TOS as a silicon precursor basically, and then through hydrolysis and condensation, we form basically a cylindrical micellar that has basically a silica hydroxide on the outer surface. And then we can basically calcinize to remove the surfactant, and we end with the silica template with a cylindrical nanopores. We can control the pore size by the calcination temperature, by the hydrolysis, condensation, and calcination temperature. We can control the particle size. The next step is basically to prepare the catalyst using this templated silica. So we adopted two different approaches. In the first one, we do a two-step. The first step is to prepare the mesocarbon material, and we use sucrose as a carbon source. We impregnate it into the silica template, and then we carbonize at 850. So now we have mesocarbons impregnated into the silica template, and then we can etch the silica template using hydrofluoric acid to end with the mesoporous carbon, and then we can impregnate the mesoporous carbon with iron precursor, and then we can hydrothermally basically reduce it to iron nanoparticle supported in porous carbon. So this is, we call it a post-confinement technique. On the alternatively, we can do a one-step impregnation of the carbon source and the iron source via sonication. And then after that, we can do the carbonization and the reduction of the iron nitrate to form iron on carbon that's impregnated in the silicate And then we can remove the silica template using hydrofluoric acid to end with a carbon iron nanoparticle assisted by sonication and porous carbon. So we have both confinement and sonication assisted iron nanoparticles. If we look at the structure of the catalyst, of course, this is the silica template. You can see the hexagonal shape has the TM has a pore size of about 9 nanometers. After formation of the porous carbon material, we get porous carbon channels with about 4 to 5 nanometer channels. And then we, with the catalyst supported on the porous carbon, you can see if we do it with the post-confinement technique, we get particles from about 10 nanometer on average, but there are a lot of agglomeration, as you can see, in multiple places. The distribution is not excellent. On the other hand, if we do the sonication assisted, we get a smaller particle size, and to the most part, maybe about 5 nanometer, no significant agglomeration, better dispersion of the iron nanoparticle. We confirmed basically the presence of iron and carbon, and of course oxygen from the mesoporous carbon using XPS. And you can see the mesoporous carbon has mostly carbon-carbon, but also there are some carboxylic groups and some maybe epoxy groups also present in the mesoporous carbon. And metallic hydrogen, metallic iron basically also present. We looked at after doping basically the metal hydride with the catalyst. We can look at the crystal structure. So this is the lithium aluminum hydride crystal structure, and identified by multiple peaks. And then the porous carbon, of course, it's amorphous material. And then after supporting, so this is the iron on gamma iron crystal structure on porous carbon. And we can see, of course, we have broad peaks because of the nano size, nano confinement effect. When we dope the metal hydride, again, the metal hydride structure becomes, the peaks becomes broader. That's indication of a reduction in their size. And if we do the release of hydrogen at 250, again, we get less structured. We still have the lithium aluminum or lithium hydride structure present, but it's much less crystal structure, of course, to the release of due to the release of hydrogen. So this was heated at 250. So we assume basically we reach to the lithium hydride formation and aluminum particle, basically an aluminum metal is formed. The morphology, the porosity was measured using VT. So the templated silica has a 750 square meter, porous carbon higher, surface area about 1,250. The metal hydride, pure metal hydride, when we supported in porous carbon at about 300 square meter per gram. The metal catalyst 650 to 820 square meter per gram, depending on the synthesis method. And then the metal hydride supported on the or doped with the catalyst has a higher than when we just supported on porous carbon. So we get 440 to 490 square meter. Pore size, you can see mostly on the porous structures, basically. So the metal hydride pore sizes didn't significantly change, but their surface area is improved. So now we'll look at the performance of the catalyzed metal hydride. So first we look at the hydrogen release. So using a temperature programmed desorption. So we test first the pure lithium aluminum hydride, we can get the typical release profile, the multi-step profile associated with the steps that we described before. We have 150-degree onset of hydrogen release. If we support it on porous carbon, we get significant enhancement because of the high surface area, the distribution of the lithium aluminum hydride. The release temperature is reduced to 80 degree, but still the onset, the maximum hydrogen release still almost at the same temperature. If we use the catalyst doping with the post-confinement approach, we reduce the onset temperature to about 76. We reduce the maximum release temperature to about 175, 180 degree. And the best performance we get it when we use the sonicated, the catalyst prepared by the sonication assisted. And we reduce the onset temperature to about 66 degree, and we reduce to the maximum hydrogen release temperature to about 150 degrees. So that's actually a significant enhancement using the catalyst with the sonication assisted technique. If we look at the kinetics, so here we're looking at the hydrogen release at 150 degree at different time. So we can see here for the lithium aluminum hydride, for the lithium aluminum hydride, after 20 minutes, we only release 0.7% hydrogen. For the porous carbon supported metal hydride, that's we release twice in 20 minutes. On the catalyzed metal hydride, that increase up to 3%, so more than 200% or 300%, 400% increase or 300% increase in the release in 20 minutes. So that means we have a rapid rate. And also the maximum of in 2 hours, we reach about 4% hydrogen release at 150 degrees. So again, the nano confinement catalyzed approach has significantly enhanced the kinetics. We can look at the release profile also at different temperatures. So we looked at 150, and then we can, here we're showing the results only for the best sample, which is with the sonicated catalyst. We did also 180, 225, 250. And of course, we get significantly increased kinetics. So we reach about 6% of hydrogen release in 20 minutes at 250, and maximum about 7% of hydrogen release after 2 hours. If we look at the kinetics with the Arrhenius plot, we can get basically activation energy of about 50 kilojoule per mole. That's about half the activation energy of the pure lithium aluminum hydride. So we basically were able to reduce the onset temperature to 66 degrees compared to 150. We reduced the activation energy by 50%, which significantly improved the kinetics, and we improved the maximum hydrogen release at fixed time, fixed temperature. Currently, we're looking at the other critical element, which is the long-term cyclability performance, and we hope to update you on that soon. Thank you, and just would like to thank Dr. MD Wahab, who did most of this work. He was a research scientist at Hamad bin Khalifa University, and also to acknowledge the funding from the Chemical Engineering Program at Texas A&M University at Qatar through the Research Impact Project. And thank you. I'll be happy to answer any questions.